Hey, honors geometry students. Welcome back to your next lesson. This is a really exciting one. This is one of my favorites. It's hard to pick just one, but this is up there. So using our knowledge of special right triangles, which you've done some work with over the last few days, right? And trigonometry, which you've done lots and lots of work with, we're going to look for some patterns, right? So that's going to mean that I'm not going to just tell you everything here. I'm going to give you some, I'm going to push you in a direction, but you're going to have some work to do on your own after this, right? And this is an awesome lesson. Sorry, I'm rather excited. Make some connections and ultimately create the unit circle. You may have heard of this. Hey, you may be able to Google it and see what it is. The unit circle is something that's going to come up and as you move forward in all levels. And it is super interesting. Like there's so many connections and that is not a highlighter. There's so many things that happen in the unit circle and I still remember learning it for the first time in geometry. I remember getting a piece of paper and filling in the unit circle. And there are pieces that you might walk away a little bit confused about after this. And that's okay. But it's really important and good for you to have experience working with it now so that you're prepared as you move forward and you're able to kind of get an even more in-depth understanding when this comes up again in algebra 2 and pre-calculus. So this is really laying a foundation and there's a lot of cool connections. So let's try to look for them. So let's start with what we already know. So you've done some work, as I said, with special right triangles, right? And that's what I have right here. Yellow is not going to work for me, is it? That's what I have right here. Special right triangles, right? And the special right triangles that we talked about were 45, 45, 90. I guess I don't really need the 90, do I? And those are the angles. And remember, this is an isosceles right triangle. And what that means, an isosceles triangle, maybe you remember way back in the year we talked about the isosceles triangle theorem, means that you've got the two legs are congruent, and then these are called your base angles are congruent, right? And that's why they're both x. And then we also have the 30, 60, 90 triangle. Right triangle, right? And we've got a 30-degree angle, a 60-degree angle, and a 90-degree angle. If you have your shortest side, sometimes I like to call this side S. So the reason that's true is literally because my geometry teacher, when I was in high school, called it S, and she referred to it as that and she would refer to it as shorty because it was the shortest side. So I don't know, maybe it'll help you because it stuck with me for all of these years. And then you would take this and multiply it by 2, and that's how you get your longest side, which is the hypotenuse. You take your shortest side and multiply it by the square root of 3, right? Not literally, like you're going to leave the square root of 3 to get your longer leg, which is across from that 60-degree angle, right? And you did some like manipulation of these. And so these are your special right triangles. These are the ones that I can have one side and I can find all of the other sides without even having to use trig. Crazy, right? Right? Yeah, I think it is. But we also have trig, right? And we're going to be using that here. So sine, remember, is opposite over hypotenuse. Cosine is adjacent over hypotenuse. And tangent is opposite over adjacent. And those are ratios of right sides. I'm sorry, right sides. That's silly. Of sides of a right triangle, right? And you may have even gone a step further and seen that, okay, well, what if my reference angle was 30? And I did opposite. Let's say I was going to find the sine of that angle, the sine of 30. Well, I'll just do it based off of this. Opposite is x over hypotenuse, which is 2x. We know how to simplify x over x. If I gave you 2 over 2, you know that's 1. X over x is just 1. So the sine of 30 degrees is 1/2. That's a fact. Like that is a fact point. Like if you went into your calculator right now and you typed the sine of 30 degrees, it's going to give you 1/2. Right? If I told you, let's find the cosine of 30 degrees. Well, let's use this special triangle. That's going to be adjacent over hypotenuse, root 3x over 2x. Well, those x's are going to cancel because they're 1. So the cosine of 30 degrees, and don't you pick up your calculator and type in root 3 over 2. You're going to leave that. The cosine of 30 degrees is root 3 over 2. If you're not convinced, if I haven't convinced you and you don't trust me, darn, but you can do this. Type cosine of 30 degrees? It's going to give you some crazy decimal. What is that? Like 0.866, blah, 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 blah. And then you're going to type into your calculator the square root of 3/2. Oh my goodness, it's going to give you the same decimal. That's wrong, right? Because they're equivalent. So that's what these special right triangles allow us to do, right? They allow us to analyze these special angles and be able to figure out different things without the need to do trig, right? It's almost like they're shortcuts. They're patterns that we recognize that are always true. So my special angles, keep in mind, I want you to remember them, are 45, 30, 60, and we care about 90, right? Okay. So we're going to put these triangles on a graph. Weird, right? If I just told you to do that, you might not know what I'm talking about, but I'm going to do it. Okay? So there's going to be one of my triangles. I'm going to start stacking triangles here. There's another right triangle. These are all right triangles. There's another right triangle. There's another right triangle. Another right triangle. Another one. Another one. Oh my goodness, how many am I going to do? Huh, do these colors mean anything? I wonder. Another one. Another one. Another one. Another one. Another one. If I kept going, if I kept adding more and more triangles, what do you think I'm starting to get or develop on this graph? I feel like someone probably said it. A circle. We're triangulating a circle. How awesome is that? Right? The more I have, the more triangles I put on this, and I'm going to just stick with these, and maybe you're aware of why I'm just sticking with these, but I'm going to get a circle on my graph. Okay? So all of these right here represent points that are on the circumference of my circle. They're on my circle. Right? And those are going to be important points for me to work with. And I want you to think, I'm not going to answer the question yet, right? I even care about these. These are called, I'm not even going to tell you yet. I want you to think about, like, why did I just do 3 in each of these quadrants? Why? Like, what are those 3 triangles? And think, because it's a little tricky, right? I said something about special angles, and special right triangles are related to this. How might that be the case? So, keeping this picture in mind, it's not going anywhere. I want you to think, well, I'm going to just tell you, all the hypotenuses of these triangles are the same. Why? Why is that true? Right? The hypotenuse is the longest side. So, I'm telling you that this is the same, and you can't really see it, but is the same as this, 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 is the same as this. Do you see it yet? The same as this. Why is that true? Because the hypotenuses all represent, now shift your thinking to the circle, all represent the radius, it's a word we haven't said in a while, of the circle. And by definition, the radius is all the same length, right? Like my radius is from the center of my circle, which, oh, neat, that's the point 0, 0, right? Keep that, you know what, I'm going to label it. All the way to the outside right here, right? Or all the way to the outside right here. The definition of a circle is the set of points that is equidistant from the center, right? The equidistant, ooh, that word takes you, we did that first semester, is all of these, right? So I'm going to take this a step further. We're going to say that it's 1. I'm going to tell you that the radius of this circle, r, is 1. Or the hypotenuse, ooh, that doesn't say or. The hypotenuses, not sure that that's the plural, I think it is, of all of these right triangles is also 1, right? They've got to be the same. The reason I'm going to pick that, why, you might ask, is because this is what we know as the unit circle, right? And so the unit is 1. I could dilate this circle, right? I could say that the radius is 2. I could say that it's 3. We're gonna treat this as what we know as the unit circle. which again, I'm going to say, hey, when you finish watching this, go Google it and see more about it. Do it. It's awesome. This is the unit circle. So whenever you are handed the unit circle, the radius of that circle, regardless of any information you're given, is 1. Like, this stuff will always hold true. Okay, so I want you to keep that in mind as we move forward in this today and in general. So we're going to focus in on quadrant 1, right? So I had this. I'm going to turn my focus to be quadrant 1. Quadrant 1 is what we know is positive, positive. Oh, what do I mean by that? Okay, well, I mean that your x values are positive and your y values are positive. Okay, so this is quadrant 1 because I would start at 0, 0. If I go, remember, you do x and then y to plot a point. So I would go to the right, which is positive, and then up, which is positive. Our goal, our first goal, we have a few goals. Our first goal is to identify these coordinates. What? How do we do that? Oh, don't worry, we have a plan. Okay, so I'm going to go one by one here. I'm going to start, you know what? We know this point. Why don't we start off with this one? Remember, it's the unit circle. So even though I don't see the rest of the circle, this distance right here, in need of a highlighter right now. That's an eraser because I'm going to erase this. Highlighter. This is the radius of the circle. This is the radius of the circle. So, in order to get from 0, 0 out to this point, I have to go to the right one, and I'm not going up or down at all. That's the 0.10. But what about to get to this? I'm going to go not right or left at all, but I'm going to go up 1. Okay? Those are called boundaries. Okay? So, now we're going to go over to this next point. And what I'm going to do is I'm going to go ahead and I'm going to redraw that triangle line. And this is going to look a little familiar. I'm going to tell you that this angle right here is 30 degrees. There's no way for you to know that until you've learned the unit circle without me telling it to you, right? But the unit circle is based around these special angles. Okay, so this is a 30-degree angle. My angle, this is called a reference angle. It's a good vocab word. And again, like, I'm giving you a lot of information, and there's some things that this is your first exposure to it, right? So it's good to hear more than less. So that's called a reference angle. Okay, so this is 30 degrees. And I want you to remember something. This is 1. Well, let's think about our special angle rules. So this is the hypotenuse. Remember, my teacher called it shorty, so I'm going to find that over here. And so this distance right here is going to be 1/2. This distance right here is going to be 1/2 times root 3, which is root 3 over 2. Okay, so now I want you to think about, like, my traveling. I'm going to go from 0, 0. How far right, how far up to get to this first point? I'm going to go to the right, root 3 over 2. And I'm going to go up 1/2. And we found the coordinates. Okay, let's keep going. Let's do the next one. There we go. And you won't always have to draw the triangles. It just helps to begin with. And then, this is going to be really mind-blowing, guys. This reference angle is going to be, maybe you guessed it, 45 degrees. I'm a little bit messy here, right? This is a 1, because that's the radius of my circle, which is also the hypotenuse. And then these two sides are equal. So if you remember, for 45, 45, 90, it's the leg times root 2 gives you the hypotenuse, right? So the leg times root 2 gives you the hypotenuse. So the leg times root 2 is going to give us 1, so we're going to have to divide by root 2. So the leg is going to be 1 over root 2. So I'm going to go to the right 1 over root 2 and up 1 over root 2. 1 over root 2, 1 over root 2. Hopefully you're still with me, even if you feel like you couldn't do this on your own right now. Okay, you might be like, wait a minute, what could this one possibly be? Well, I added 15 degrees on. I'm going to add 15 more. What does that give me? 60. Okay, so We already know this one. This is 1. My shortest side, I'm going to take that and divide it in half, right? If this angle down here is 60, this one up here is 30. They're complementary. You know this stuff. So this is going to be 1/2. And then we're going to have to go over, right? It's just going to be the reverse of this one. So I'm going to be going over 1/2 and then up √3/2. And just like that, you've used special angles to identify all of the special angles in quadrant 1. I want to go a step further, and I want to ask you guys a question right now, which I asked this already. You already identified what the sine of 30 degrees is. Maybe you remember. Let's go back to it. No, it's going to take me like a year. I'm not going to go back to it. I changed my mind. It sounded better in theory. So the sine of 30 degrees. So let's focus in on just this triangle right here. This first one that we drew that had a reference angle of 30 degrees. Right? And so the sine is opposite over hypotenuse. This is nice because we know the hypotenuse is 1. And the opposite side is 1/2. So I get that the sine of 30 degrees is 1/2. Well, do you see anything interesting over here with this point? Maybe you see that it's the y-coordinate? What if I asked you for the sine of 45 degrees based off of the special triangle? Well, that second one was 45 degrees. Sine is opposite over hypotenuse. My hypotenuse is still 1. That's why this is working. When I go opposite, it's this side, which was 1/√2. Anything divided by 1 is just itself. My goodness, that could have been either one, but that was the y value. What if I asked you for the sine of 60? Opposite over hypotenuse. So if I look at that last triangle I drew, opposite was √3/2. Hypotenuse is still 1. I get √3/2. Oh my goodness. Right? When we're going opposite of these reference angles, we're just getting the height, right? That vertical height, which is your y value, right? Height, y goes up and down, height goes up and down. Very interesting. So what do you think might be true with cosine? If I asked you for the cosine of 30 degrees, that's that first one. Well, that's going to be adjacent over hypotenuse. The hypotenuse is 1. So adjacent here, it was this length. I think it's written right here. I got pretty messy. √3/2. So I get √3/2, which, oh wow, that's the x value there. So the cosine of 45, I should get 1/√2 if this pattern is true. That rhymed. That was awesome. Over 1. So that second triangle I drew, adjacent, yeah, that was 1/√2. That was one of the legs of my triangle. So I get 1/√2. So again, if this pattern holds true, I get the cosine of 60, I should get 1/2, right? Well, the adjacent side down here was in fact 1/2 over 1, which is 1/2, right? So these coordinate points, which we know as x, y, wow, that's just the cosine of my reference angle times the sine of my reference angle. I'm sorry, not times, sine. X is cosine, y is sine. Huh, that's pretty cool, right? I think it's pretty cool. So if all of this is true, what happens? This is just 0 degrees, right? This was 0, this was 30, this was 45, this was 60, this was 90, right? That's where we get to like the 90 degrees. We're always starting from this positive or x-axis. So if I asked you for the sine of 0 degrees, and this is all true, I should just get 0. Try it in your calculator, do you? Checks out for me. What about the cosine of 0? I should get 1. Checks out for me. What about the sine of 90 degrees? I feel like we've done that one. You should get 1. The cosine of 90 degrees, you should get 0. There's a lot. This is not something you need to memorize, right? This is your first experience with this. I think. You can tell me otherwise. You can tell your teacher otherwise. Let's see. Did I want to do anything else on this page? I didn't. We're gonna now go in a different direction. And I'm weirdly enough not gonna do quadrant 2 with you guys right now. We're actually gonna skip ahead. We're gonna look at quadrant 4. Right? So I want you to remember, and I might go back, before we worry about like doing all the math, let's just think about what we already did. Right? If I know how reflections work. I know those things. This is quadrant 4, right? This is quadrant 1. This is quadrant 2. This is quadrant 3. This is quadrant 4. We go counterclockwise, and hopefully you can make the connection from when we did rigid transformations that a positive rotation is counterclockwise, and a negative rotation is clockwise. So if we go to the left, it's a positive rotation. If we go to the right, it's a negative rotation. So we already know this point, right? That was 1, 0. I feel like you guys can know this point. It's going to be 0, -1. Think about what this point in quadrant 1, where was that, right? This was, if I draw my triangle in, this is a 30-degree reference angle. You know, it's not actually a 30-degree angle because I'm going here. So I'm going all the way around this way. What's that angle? Oh, 360 minus 30. I'll do more of this in a moment. That's actually 330 degrees. And what's really interesting is if you do the sine of 30 degrees in your calculator and the sine of 330. Oh, no, I guess that's not what I meant. -30 because you're going the other way. Right? You would actually get the same thing. That's beyond geometry. But that is an interesting connection to make, in my personal opinion. Sorry, I got off track there a little bit. So let's think about what we already know about a 30-degree angle. Well, the 30-degree was right here, √3/2, 1/2. So I'm still going to be going over √3/2. Now I'm going to be going down 1/2. This is going to be √3/2, 1/2, -1/2. Right? All my y values are going to become negative. Remember when you reflect over the x-axis? Ooh, coordinate notation. xy becomes, x stays the same, y becomes negative. So what do you think happens when we get a 45-degree reference angle down here? Okay, well, let's go back and reference what we have. That was 1/√2, 1/√2. So this is going to be 1/√2, -1/√2. So you can imagine, what might this look like in quadrant 2? What might this look like in quadrant 3? Those are things that you're going to be doing. And then we can get to our 60-degree angle. Right? Okay, so this is 60 degrees. Well, let's reference what we already have. Here's my 60 degrees. It's just going to be a reflection down here. 1/2 √3/2. So 1/2 -√3/2. This quadrant, both are positive. This is negative positive. This is negative negative. This is positive negative. Right? You probably didn't need me to tell you that, but that's something that's sometimes good to know. So just based off of our pattern before, if I asked you for the sine of 330 degrees, that's this angle right here, you would get -1/2, and you can check that in your calculator. If I asked you for, what's this angle measure? Right? Even though it was a 60-degree reference angle, I'm actually going to be going from here, and I'm going to be going all the way around to this way. So I'm not going to be going 60 degrees. I'm actually going to be going 360 minus 60. I'm actually going to be going 300 degrees. And we'll fill those all in the next slide before I leave you guys. So if I asked you for the sine of 300 degrees, that's right here. I'm looking at the y value. I would get -√3/2. What about if I asked you for the sine of, what's this angle? 90, 180. Maybe you need your calculator. That's okay. 270. The sine of 270 degrees. That's going to give me -1. Pretty neat, right? So let's fill this in, and I kind of already made some of the connections, but let's fill some of these in. I'm going to start with the angles, okay? So we're going to go around. So this is going to be 0 degrees. This is 30. I'm going to fill in my 30s first. This is 60. This is 90. This is, just keep adding 30, 120. Right? You can see what's happening between these. This is 150. Does this make sense? This is 180. Sure. Okay. This is 210. I'm just adding 30. This is 240. Can I fix that? I was looking so nice. This is 270. That makes sense. And then we've got 300. Oh, we said that one. And then we've got 330. And then we made a full rotation. I can even call this 360. Okay. Let's now fill in the 45s. Right? That's these increments. 45 degrees. That's 90. This is 135. This has a reference angle of 45. Right? If I draw my right triangle in here, and I'm going to do this, that's horrific. Don't judge my right triangle. This angle right here is 45. It is a 45, 45, 90 right triangle that I'm dealing with, but the actual angle is 135, right? Because you're always going to be starting over here. As weird as that is, as unnatural as that may sound, you always are going to be going back to the start. You just use the reference angles to help to make those connections of this is really a 45-degree angle in quadrant 2. Okay, sorry. So if I add 45, I get to 180. I add 45, I get to 225. I add 45, I get to 270. And I add 45, and I get to 315. Right? You can also see that this is halfway. I'm adding 15. And I'm adding 15. I'm adding 15. Okay, so I've got my angles filled in. We also figured out these coordinate points. Right? This was, hopefully you remember, was root 3 over 2, 1/2. This one was 1/2 root 3 over 2. This one was 0, 1. This one was 1, 0. This one was 0, -1 down here. And then the 45-degree angle was 1 over root 2, 1 over root 2. They're the same because it's 45 degrees, right? It's 45, 45, 90. Okay, and then we did quadrant 4, and we realized we saw this pattern here, and we realized it's just a 30-degree angle. It's in quadrant 4. And what happens is that your x stays the same and your y becomes negative. Oh, I wrote it incorrectly. Right? So your x stays the same and your y becomes negative. I know square roots scare us sometimes, but you guys can handle it. 1/2 negative root 3 over 2. Right? And those are the pieces that we've gone through. Okay? We also said that the sine of theta, that'll be your reference angle, right? Or the theta will be the angle, angle of rotation is what I'll call it. Angle of rotation. The sine of theta is just going to be your y value. And the cosine of theta is just going to be your x value, right? So that point xy is just the cosine sine, right? Pretty cool. Neat, right? And so you can think about like, how does this relate to all of, and this is just for special angles. There's no other angles. Like the ones you're looking at are the ones that the unit circle is used for. You're never going to be thrown a 15-degree angle. It's not going to happen. It's not a special angle. Okay? You might cross things where we build off of this. It's still not a special angle, but you learn how to find them using special angles. That's a pre-cal thing. Okay? So you've got time. The last thing I wanted to point out is we have, let's say I have a right triangle. Okay? That's really what we have. We've triangulated this circle. So I have this, and we know that this side length is 1 over root 2, and this side length is 1 over root 2. And this is 1. And if you recall at the very beginning of this, I talked to you about how the definition of a circle is the set of all points that are equidistant from the center, right? And in this case, that length is 1. So we know if I have two sides of a right triangle, I can use my favorite theorem, the Pythagorean theorem. He's always around. A squared plus B squared is going to equal to C squared, right? That's how it works for a triangle. If I square this, I know this seems unnatural, I get 1/2. Plus, if I square this, I get 1/2. The square root of 2 squared is 1/2, right? I'm sorry, is 2. It's like you do something and undo it. Equals to 1. So I get 1 equals 1, right? So I really just did, these are just my x and y values. So I really just did x squared plus y squared equals to, well, that was the radius squared. Okay, let's go one step further. This is really where I want you, but I'm going to go one step further. We said that x was sine. Sine squared, well, like a sine of theta squared, plus cosine of theta squared equals to, what is r? It's 1. It's always 1. This is the unit circle. Equals to 1. I'm way ahead of myself, but I just want you guys to see where this eventually goes. This is what's called the Pythagorean identity. You will use it in the future. It's worth thinking about how this all connects. Okay, and I know many of you guys are intrigued by this. Like, look it up. Come in and ask us more questions about it, because this stuff is, there's a lot of connections, and you can see, like, even through this video, there's things that we did first semester that are important, and they come up, even if they're just like little things and little terms and vocab and those rigid transformations. Just really, it really all ties together. It's beautiful. So your job, you've got an assignment where you're filling in the remainder of the unit circle, right? I've given you, we did together quadrants 1 and 4. Quadrants 2 and 3 are really your job, and you're creating your first unit circle, just like I remember doing in geometry way back many years ago, right? So you have that assignment, and there's some follow-up questions on it. So have fun with it, explore, look at it, analyze it, like, ask questions. This stuff is awesome. So other than that, that's all I got for you guys. You really put yourself in this, and hopefully Sol has special right triangles and trigonometry can apply and what these patterns are and making connections to really ultimately create your first unit circle. So congrats, and we will see you all soon.